So let's try to recap something we did last time, which is the Gibbs phase rule. Gibbs phase rule says that the number of degrees of freedom, number of intensive quantities you can vary independently, that's the keyword, is C minus P plus 2, where C is the number of components in the system, P is the number of phases. So let's try to understand this by looking at an example. Okay, so I'll draw something and I would like you to tell me whether it's correct or not. Camille, like this morning I woke up thinking, I have not yet asked Camille a question. So this one's for you. Yeah. Okay, so Camille, you have to tell me when I make a mistake. Sorry for the pressure. I make a lot of mistakes, so it's not too bad. So this is pressure, this is temperature, and we are going to look at a one component system, okay? So I drew a line, and I drew another line, and I drew a line over here. My claim is this region over here is a single phase region. Is that consistent with Gibbs phase rule or not? Let's just work through the math, Camille, okay? So we have F is equal to C minus P plus 2. So, and this is a one component system, okay? Everything would change if depending on whether it was 1 or 2. So what is the value of C? One component, right? And I shaded an area. So what is the value of P? Huh? The number of, sorry, what is the value of F? The number of degrees of freedom. It's area, so it's 2, right? In this area, you can vary pressure and temperature independently. So degree of freedom is 2. And I wrote alpha, single phase. So P is equal to 1. I feel like I answered your question. That's okay. And then plus 2. So this is correct, right? Okay, Camille, you're not done yet. Now I say that, oops, sorry about that. Let me remove this part. And I'm going to draw more lines. And what I want you to do, Camille, is to tell me where I will make one mistake, exactly one mistake. I know. It's terrible. Okay, so the mistake, and the question is only for Camille. And it's a one component system. And I'm going to mark phases. And then I would like you to tell me where is the mistake. This one is phase beta. This one is phase delta. This one is phase gamma. This one is phase epsilon. This line in the middle is joint alpha plus gamma. This line over here is alpha plus delta. This line over here is beta plus delta. This line is beta plus gamma. This line is gamma plus epsilon. This line is epsilon plus delta. And this point over here is alpha plus beta plus gamma, right? It's at the intersection of all three. So for example, if alpha was India, and what does India have in neighbors? Beta was Nepal and gamma was China. This would be Tibet or something like that. I should be careful in making such jokes. And this point here is alpha plus beta plus delta. And this point is beta plus gamma plus epsilon plus delta. And in this phase diagram, for a one component system, there is exactly one mistake, Camille. Which is the mistake? Maybe there is none. Anything more than a triple point should not be there, right? So beta plus gamma plus delta plus epsilon is not correct. Everyone agrees with Camille? Camille gets a chocolate. I have a lot of Halloween candy. Halloween was Pakora's busiest night in the year. Even Craig stopped dinner. He was like, who are these people? Well, which one do you want? Huh? Did Pakora dress up? Yeah. No, but he's going to dress up tomorrow. Because tomorrow it is 5th birthday. So I have to buy his birthday babe, and birthday hat. I will send photo, don't worry. And his friends will be over, brownie and latte and hazel, and they will all have birthday cake. It's a special day. I'm very emotional. Okay. So, but if this was a two-component system, then this could happen, right? You could have quadruple points. So you can read phase diagrams, and I could have made similar errors if in this area, if I had written this is delta plus and delta prime, that's also not possible, right? Because it's a single. So Gibbs phase rule really tells you what's going on. You can look at it and check things. So this is not possible. This is not possible in a one-component system. Okay, good. Thank you, Kamil.
Like just from the equation, you can see that f cannot be
-1.
Yeah.
So now what we are going to do next, and this connects to one of the problems on the homework, is to really think about characterizing phase boundaries. So I drew curve here, right? I said that the boundary between epsilon and gamma is this line over here, right? And as you move from this line, at any point, you are undergoing a phase transition. You're moving from alpha to gamma. So I want to characterize this boundary. What is this? What is the curve? What is the mathematical curve giving this? How can we measure this through experiments? That's what I want to do. And then once we do that, we will talk about ice skating and see why the common sense explanation of ice skating is actually wrong. So the topic we are going to do next is how do we characterize phase boundaries. And in order to do this, all of this is going to be talking about when control parameters are pressure and temperature. Okay, so we will always be thinking about Gibbs free energy in any of this. So let's say we have a pressure temperature phase diagram. In this, we have some generic phase boundary that looks like this. Okay, here we have alpha, and here we have beta. And along this boundary, alpha plus beta coexist. Okay, they can happily exist together. They can be in equilibrium with each other. So what I want to do is to write down an equation for this curve in terms of something that can be measured experimentally. Okay, so let's consider 2 points on this curve. Let's consider point A and let's consider point B. Here I have drawn point A and B very far from each other, but in reality, we are thinking about point A and B very close to each other. Okay, small change along this curve. Anytime you describe a curve, you are interested in still small changes around the curve, what goes on. We want to find the slope of this curve at a given pressure and temperature. So now let's imagine that two phases, as is clear from this diagram, two phases, alpha and beta, both are in equilibrium in a one component system. So we are talking about a one component system. It can be generalized to higher components, but for now we'll just stick with one component system at points A as well as B. If two phases are in equilibrium, what quantity should be equal? What is the second law of thermodynamics for phases? Undergrad. You were here last class. Yeah, there you go. Chocolate is waiting for you. Chemical potential, there you go. Okay. So chemical potential, says the undergrad. So chemical potential of alpha, phase alpha, at a given pressure and temperature should be equal to chemical potential of phase beta at that pressure and temperature, right? This is the second law of thermodynamics for phases. So furthermore, this should be true both at points A and B, right? They are at equilibrium at both points. So this should be true both at A and B. So if I want to write down the change in chemical potential of phase alpha as we move from point A to B, the change in chemical potential of phase alpha should be equal to the change in chemical potential of phase beta, right? If they were unequal, then that's like you're saying they were equal at A, now they change by a separate amount, then they're not going to be equal at B, right? So this change must be equal. So d mu alpha should be equal to d mu beta. This is a single component system. Here's another chocolate question. How do I connect this to Gibbs free energy in a single component system? What should I do? Who is, yeah, go ahead.
The partial Gibbs free energy is mu.
Partial, I don't want to use partial derivatives. Even simpler. It's still is different, right? So molar. So what should I write? What does this mean for G of alpha?
Mu of alpha times n.
N, right? So if you're keeping the number of moles constant, then what does it mean for G of alpha?
So d mu is
dg, right? So because G is equal to mu n in a generic system, if you have many components, if you have k components, G is equal to mu I ni, right? This is very special about G. A does not follow this. This is a homework problem. You should be able to prove why A does not follow this. For one component system, G is equal to mu n, right? It's a one component system, so n is constant for construction. There is no chemical reaction going on here, right? So this is the same as dg alpha is equal to dg beta. So I could have just written down in one line, but I want to make a point that this is true only for one component system. If it was two components, you won't be able to do that, right? You will have to be careful in that one. You will have to worry about mole fractions. Okay, what should I do next? What do I know about dg? How do I write dg in terms of pressure, temperature? So Vadeep, how do I write dg in terms of dp and dt?
dDP minus SdP plus dP.
Okay, correct. You play cricket? Huh?
Obviously.
Obviously. No. Okay. So dg is equal to vdp minus sdt plus mu dn, but we are talking about single component system, right? So there is no point in talking about, there should be a plus mu dn, but that goes to 0 because this is a one component system. There is nothing going on. So in other words, now let me number the equations. This is equation 1, this is equation 2. We can put equation 2 in equation 1, right? Let me write down both of them again on the next page. If you haven't copied, don't worry. So equation 1 is dg of alpha is equal to dg of beta, and equation 2 is dg is equal to vdp minus sdt. So how do we write down 2 in 1? We will have volume of phase alpha multiplied by dp, right, minus entropy of phase alpha multiplied by dt is equal to volume of phase beta multiplied by dp minus entropy of phase beta multiplied by dt. And here we have assumed that it's a small change. Why is that important, Shah? Why would this equation be wrong if the change was not small? What would I have to do?
What is on the slope on the here?
You have to be careful about the value itself, right? The slope and everything, it would be some sort of integral. I mean, you answered, yeah. So, okay, let's go from here. So now what we can do, we can say, we can rearrange this. V of beta minus V of alpha multiplied by dp is equal to S of beta minus S of alpha multiplied by dt, okay? Or dp by dt, the slope. Remember, what are we trying to do in all of this? Let me draw the phase diagram again. We have pressure and temperature, and we have phase alpha and beta. At that given point, we want to characterize this curve. We want to write down the slope of this curve, okay? So that slope is S beta minus S alpha divided by V beta minus V alpha. You could also write it as S. This is the same as S alpha minus S beta divided by V alpha minus V beta, right? whichever direction you go in, you just have to change both numerator and denominator. In other words, without using alpha and beta, this can be written as dP by dt is equal to change in entropy during the transition divided by change in volume during the transition. And this is what characterizes a phase boundary. We derived it for one component system. That's what we do it for two component. You can derive something similar. It will be slightly more complicated, but we'll stick with one component. This is very important. This equation has a name. It's known as the Clapeyron equation. At the end of this, towards the end of this class, we will derive something known as Clausius-Clapeyron equation. There is a ton of literature out there on the internet and even in textbooks which say Clapeyron equation or the Clausius-Clapeyron equation. That's complete garbage. Clausius-Clapeyron equation is a simplification of this equation that applies for ideal behavior. This equation, we did not assume anything ideal, right? It's very, very generic. If it's one component and you have a phase boundary, it's going to apply in equilibrium, right? That's the thing. So it's a very powerful equation. So during a phase transition, yeah.
What was the argument for like choosing dP? Like what happens?
Because slope is about small changes, right? At any slope, it will change. It will be here. This will be different. We are talking about small changes. At any point, it will be different.
Yeah, but if we were to take 2 points that are very far away,
Then it doesn't make sense to talk about a slope, right?
yeah, not as a slope, but like the difference in.
It won't be useful. That's the only, you could do it. It won't be useful. It won't be the slope. Slope in math is defined by small changes, right? So you can always do that, but it will be some change, right? So what you are defining, if you have a boundary like this, you could talk about dP by dt between here and here. But there is no physical significance to that change, right? From the green arrow. It doesn't tell you anything about the curve. It tells you how much it changed if you went from A to B. So you can do it, but it's not useful. That's the only thing. So this is Clapeyron equation. How would I go about measuring it? Volume is easy to measure, right? There is a phase transition going on. You see how much volume changed. How would I measure delta transition S? Any ideas? Oh, good. Tell me more. How exactly? But tell me the equation. Now, for the chocolate, you have to be more precise. Is it just delta Q? No, I'm okay with this. But delta Q, does Q have a subscript or not? Remember Clausius inequality. It has to be reversible. In general, it's going to be bigger or equal. But if this is reversible, then it's going to be equal, right? So if you can measure the heat that is going during the change, during the phase transition in a reversible manner, then you have your delta S transition by T. Then you have delta S transition, right? In other words, we can write down dP by dt is equal to delta. Let's talk about delta P by delta T because we are using delta both sides. That is so, and this is reversible. That's very important because if it's not reversible, you know this is not true. It's going to be an inequality, right? That's Clausius inequality. So delta P by delta T is equal to delta transition S by delta transition V is equal to delta Q reversible during transition divided by the temperature of the transition and the volume change during the transition. For most problems, the delta Q reversible. So this is also Clapeyron equation. For many physical problems, delta Q reversible is known as the latent heat, right? And that depends on the particular phase transition that you're talking about. If you're talking about vaporization, going from liquid to vapor, then it's latent heat of boiling or latent heat of vaporization, right? It could be latent heat of fusion if you're talking about solid going to liquid, right? So depending on what you have, it's known as the latent heat of that process. So latent heat is generally denoted by the word L. So this is going to be L by T delta V. All of this is Clapeyron equation. each of any of these is equivalent. And that's what we are going to use next to understand. Well, it won't help us understand ice skating, it will help us debunk a common idea about ice skating. Everyone happy with this?
Small question.
Mhm.
If you go back, when we put DG in for TMU,
Mhm.
we did a product rule on the GMU and then DN was just.
Yeah, so what we really did, let me write it down carefully. What we did is to say, therefore, dg alpha by n is equal to dg beta by n. And n cancel. It's the same n. Because
Okay.
n does not change.
Yeah, that's fine. I'm saying from like G equals mu n for the one component system.
Yeah.
Then you did a like product rule there, and then you were like DN is 0.
Yeah.
Going.
Yeah.
Okay. I just want to double check that.
Yeah, sure. Good. So now let's talk about ice skating. And I think it was Ben last time who told us that he believes. What was your belief about ice skating, Ben?
I was told by someone sometime maybe that it's due to like a layer of water, caused by pressure or something.
Yeah. So how thick is it layer? That's the question.
Not very thick.
Not very thick. So I will post some articles online, but the common sense idea about ice skating is you apply pressure through your ice skates, right? And it causes localized melting. There is a local layer of water and you go through it. And I will show you by the phase diagram of water that that's not possible. The amount of pressure you will need is extremely high. You will have to be an elephant wearing ballerina shoes. Then that might be correct. So how does ice skating work? It's actually still localized melting, but it's more complicated. It's not equilibrium thermodynamics. There's literally a nanofilm of water that forms. So if it was purely melting, it shouldn't have to be one or two layers of water, one or two atomic layers of water, right? It should be more than that. So in reality, there is, but it's like a nanofilm. And people still fight over this, about how exactly ice skating works, believe it or not. So let's try to understand this. In order to do this, we will draw the phase diagram of water. And now we will be a bit more quantitative. So the phase diagram of water looks something like this. This is pressure, this is temperature. You have a solid region over here, and we're talking about pure water. You have a liquid region over here, and you have a vapor. Okay? So now let's think carefully. At 1 atmospheric pressure and 0 degrees Celsius, what is the stable phase of water? Chocolate. Sanjana. Solid. Are you sure?
No, actually, it would exist in equilibrium as solid and liquid.
Exactly. There you go. So, yeah. So that's important, right? So it should be somewhere along this curve, right? It can't be deep in any phase. 0 degrees Celsius is where it exists in equilibrium. So this, it could be 0 degrees Celsius and 1 atmosphere. What is the temperature in an ice skating rink? Is it higher than 0 degrees Celsius or lower? Huh? It's way lower, right? You keep it. What? You think it's higher? Oh my God.
You mean like the stadium? Or do you mean
The
like,
ice itself.
the ice?
The stadium also. What is the
Yeah.
temperature? I think it's colder. People wear jacket. I haven't
Yeah,
seen
but
people
it's
inside.
It's still below 0.
Oh, it's definitely below 0.
The stadium? No.
The ice.
The ice?
Yes.
That's what I'm trying to say.
Now she's raising deeper questions. So this means maybe we are out of thermal equilibrium, right? So that could lead to more problems. But we are just going to talk about the ice, right? So the typical ice skating rink temperature is around minus 7 degrees Celsius. It's just slightly colder. Of the skating rink, okay? Typical temperature of skating rink. So what is the pressure? Normally it should be 1 atmosphere, right? But when you have ice skates on, you are applying higher pressure on it, right? So normally it should lie along this dashed line. So where would that lie? That would be somewhere over here. So I'm saying something common sense, right? If you stay at atmospheric pressure, like Sanjana pointed, if you're at 0 degrees Celsius, you are at the boundary between solid and liquid, right? You are in equilibrium. But if you keep decreasing the temperature, solid will become more and more stable, right? If you went to the right side, liquid will become more and more stable, right? That's the idea. So what you want to do now is to apply pressure through your ice skates so that you get up to this point, right? That's what you need to do. And this also shows you why they have to keep at minus 7 degrees Celsius. If the ice skating rink surface was minus 50 degrees Celsius, would you need to apply less pressure or more pressure? More pressure. And you can see it from this one, right? It would be this line over here. You would have to apply enormous amounts of pressure. So let's try to calculate this value of delta P. How much pressure do you have to apply through your ice skates for this to happen? And you don't want it to be much warmer than minus 7 degrees Celsius, because then it won't be ice. It would be liquid, right? You will be like, if you fall on it, you will get really, really wet. And that's not good. So how do we do this? What we are going to use Clapeyron equation, okay? So we want to calculate delta P. We know delta T in this case, the delta T is 7 degrees Celsius, right? And when it comes to change, Celsius and Kelvin are the same thing, right? So 7 Kelvin change is what we are talking about. So delta P by delta T is equal to L by T delta V. That's the relation we are going to use. So I'm going to provide you some numbers. T is minus 7 degrees Celsius. How much is that in Kelvin? 266, 267, right? 266 Kelvin. Latent heat of fusion of water. Why do you remember that?
I do this.
80 kilojoule. Well, the number I have is a bit larger than that, but it doesn't matter. We can use 80 kilojoule if you say that.
I don't remember.
See, so we won't trust you then. The one number I have here is 3.34 into 10 to the power 5 joule per kg. So it's around 100 kilojoule, right? So you're in the right benchmark, right? So this is 300 kilojoule. So from a physicist perspective, it's the same. So the important thing is this is positive. Does that make sense? In order to melt ice, do you have to cool it or heat it? Heat it. Is this true for all materials that you have to heat them in order to melt it? It is, except one funky thing. That's helium-3. It's a superconductor. And that's very crazy. You have to cool it in order for it to melt. And it's still not clear. You know, as you saw this summer, everyone went crazy over superconductor, right? So helium-3 is very, very complicated. Apart from helium-3, L is positive for everything else. That's L. How about delta V? For melting ice. When you melt ice and water forms, is it going to be positive or negative? Negative. And this is where water is very, very special. For everything else, this is positive. When you melt something, in other words, solid tends to be denser than liquid, right? That's so you right. We were talking about crystal packing last time, right? Solid means you pack it in a nice crystal, it's going to be denser. Water is this funky thing due to hydrogen bonding that it actually is lighter in liquid form. So delta V is negative, and delta V is, when I say negative, I really mean V liquid minus V solid. And that is, I will give you the number, is minus 9 into 10 to the power minus 5 meter cube by kg. Okay. So first of all, this already shows you why the slope for this liquid solid boundary is negative, right? L is positive and delta V is negative. So the slope is going to be negative. And we will study this slope in a minute for generic systems, and we will see why it is. Yeah, we will look at that in a moment. For water, you can see this is what it is. So let's calculate delta P by delta T by plugging in these values. So delta P we need to calculate. Delta T we know. So delta T is 7 Kelvin, right? So we put delta T is equal to 7 Kelvin multiplied by L, which is 3.34 into 10 to the power 5, divided by temperature, which is 266, multiplied by volume change, and the whole thing is negative.
Where's the 7?
That's delta T.
Oh, I see.
Okay, but delta T is also negative. So negative, negative cancel out. We have to be careful. So delta, yeah, it's good that you asked. So delta T is equal to -7. So this thing is -7 Kelvin. And in the denominator, we have 266, which is the temperature multiplied by delta V. That is -9 into 10 to the power -5, right? So there's a bunch of numbers here, but you can see what's going to dominate, right? In the numerator, you have 10 to the power 5. In the denominator, you have 10 to the power -5. That's going to give you 10 to the power 10, right? But then you divide it by another big number, 266 and 9. So the whole thing comes out to be something like 1000 megapascal. What is atmospheric pressure in megapascal? Anyone knows? I also don't know. I have it written. Anyone remembers? It's around 10,000 pascal. It's around 0.1 megapascal. So how many atmospheres are we talking about here? 10 to the power 4 atmospheres. That is the pressure you need to apply. That's enormous. That is not the pressure you generate through your ice skates. So this shows that this debunks the localized melting ice skating story. And I have to say in quotes because it debunks the equilibrium picture. In reality, there is a nanofilm that forms, but it's not really melting in a traditional sense. It's a bit different. Okay. So I show this example for other reasons also. Another example I like to show is we have a bunch of Indian students in the classroom, so they will relate to it. So when you come from India to US for grad school, at least when I came, every parent wanted to, like when you go to grad school, when you leave home, right, your parents want to pack off things, right? Your special things like take this, take that. In India, there is one special thing which no one else packs up, but Indian parents do. Pressure cooker. And you never use it. Maybe you guys do, but I never use it. It's terrible. It's like, yeah, anyway, it's like a hazard. But the idea in a pressure cooker is you cook something quicker by applying pressure on it, right? So I'm going to give you almost certainly more than 50% chance a problem in the final exam where you will be using Clapeyron equation to understand how does a pressure cooker work. Okay, so go and look at it. Same thing. You look at the boundary and you see what's going on.
This calculation that we used, was it at 0 degrees Celsius or at?
It's approximate. It's approximate.
Also, just for clarification, the latent heat is a function of the temperature.
Absolutely. It is a function. That's why we are talking about small changes like -7 degrees Celsius. These are all approximate, strictly speaking. But the numbers won't change, right? Okay, any questions about this? Yeah.
Why you say this is not like
If it's not in equilibrium, then we can't use G and mu and all these concepts, right? Everything goes away. If ice skating was a non-equilibrium process, then 684 is not going to help you.
Yeah, I'm asking why it's not.
Because an equilibrium picture does not explain it, right?
Sure, but why in reality it's not?
Oh, that I will send you the article and you will see. This is my friend in quotes, David Limmer at UC Berkeley. He is quoted. I think the article is from like Atlantic or something like that. Ice skating is not what you think it is. You can read or talks about it. Yeah, remind me to post that on Slack. Okay, go ahead.
So you pointed out the pressure is very high. So the pressure is technically force per area. How much area is touching the ice also matters.
Yeah, you can do the math. You can look at the area of an ice skate and you will see it won't get you to this much pressure.
You can get it to the 1 cross 1 centimeter, but I don't know how much of it actually touches when you play.
Yeah, it doesn't get you there. Nope. So I will write down in red. This is elephant in ballerina shoes. I did the math and I saw that it's what it is. I took the weight of an elephant. But yeah, the ballerina shoes will be around your 1 centimeter by 1 centimeter thing, right? Okay. So what I'm going to do next is to look at, so we drew the water phase diagram, right? And how many boundaries did we have here? We had the solid liquid, the liquid vapor, and solid vapor, right? The solid liquid boundary corresponds to melting, liquid vapor corresponds to boiling, and solid vapor corresponds to sublimation, right? So let's look at these three boundaries more generally and see what we can say about them. So let's look at solid liquid, liquid vapor, and vapor solid boundaries, not just for water, but for general systems. For generic systems, one by one. Okay, so first we start with solid liquid. And again, we are going to use Clapeyron, Clapeyron equation one by one. So solid liquid, what is Clapeyron equation? Clapeyron equation, generally speaking, is dP by dt is equal to delta S by delta V. And we said, Maria Delia said that delta S you can get from heat. So that is L by T delta V. And solid liquid, the change is known as fusion, right? So if the process is happening at a constant pressure, that's what makes Clapeyron equation even more useful. We talked about reversible change. But if the change is in that of a state function, then you don't even need to think about reversible or irreversible, right? If it's a state function, it just matters what is the endpoint. And if it is a constant pressure change, then what is delta Q equal to at constant pressure and temperature? Is the change in enthalpy, right? Delta Q is equal to dH at constant pressure and temperature, and that's what makes it super useful. So this thing will be given by delta fusion of H. So this is known as the enthalpy of fusion, okay? And this is something you can just report, you can look it up in tables. You don't need to do it reversibly or reversibly. It really depends on the starting point, on the end point. It doesn't matter how you did it. You start from, if you're equilibrated, you do something, you cause it to melt, highly non-equilibrium, that's okay. At the end point, you allow it to equilibrate and you measure the change, okay? Wow, look at this noise.
That vibrations.
Yeah. Small earthquake.
So if we're at constant pressure and temperature, is dP by dt not 0?
Good point. Lydia tries to trick me. No, we are talking about the slope when the change is happening at this pressure and temperature. That's what I mean by it, okay? It's tricky. It's, I was waiting for someone to ask. Could you? So we are talking about this slope when the change happened at point X, okay? That's what it is. That's why we can.
0 over 0, but the ratio is fine.
Yeah. So delta fusion H by T delta fusion V. And as I mentioned earlier, delta fusion H is positive for almost everything except helium-3. I don't know if helium-3 is still resolved. I remember reading about it in like Feynman lectures. There's a chapter on it, or even like, surely you're joking, Mr. Feynman. It's so many books, people talk about it. But it's a superconductor. People don't really understand superconductors, right? That's what it is. So this is going to be positive for most of the chemicals you are probably going to study in your PhD or in your research. If it's a superconductor, good luck for many reasons. And delta fusion V is also generally positive except water, okay? So what does this tell me about dP by dt for most materials except helium-3 and water? Is it going to be positive or negative? Positive, because numerator is generally positive, denominator is generally positive. What about temperature? Murray, last chocolate's got your name on it. So this thing, delta fusion H is positive for most materials except helium, okay? Delta fusion volume is positive for most materials. How about temperature? Is it positive or negative? Huh? Why? Depends on the unit, right? Are we going to be Americans and use Fahrenheit? Or are we going to be scientists and use Kelvin? Kelvin, right? There you go. So, oops, in Kelvin scale, it's always positive, right? And that's what we showed. Remember the postulate, partial S by partial E is positive, right? That was the postulate, right? So temperature is always going to be positive. We're not going to use Fahrenheit scale. So dP by dt is positive for most materials. dP by dt is negative for water. So if we look, wow, this is noisy. If we look at pressure versus temperature, water is going to look something like this, right? It will be negative. While almost everything else, except helium-3, so that's why I say almost everything else is going to look positive, rightward facing, right? And it's fundamental to life, the way it exists, that water has this behavior. Otherwise, like there are in Siberia, people have found some lakes which have never melted from the top, ever. Like there is no record that these lakes have ever melted. And it's full of life inside it, in the water. It's crazy, right? These are things that have never ever seen direct sunlight, and they still exist. And the reason that happens is because ice goes to the top, right? Is anyone here who likes to go camping in the snow? No one? Come on. You should do it. You're in PhD. You should gotta do some stupid stuff. I used to do it a lot during grad school. And there in California, I would go up to Mount Whitney and places like that where it gets really, really cold. And when you carry your water, it's very important to carry your bottle upside down. If you don't carry it upside down, the ice will form and go to the top of the water bottle, and then you can never open it, right? So you have to carry it upside down, so the ice always forms on the bottom of the bottle. So it has great practical implications for camping in the snow and also for life in general. So that's the solid liquid boundary. Now let's go. Any questions about this one?
Yeah, just can we say anything about the second derivative? Like,
Oh, you're going to do that in the homework, I think.
Oh.
That's about second order phase transitions. But generally speaking, I don't know. I don't know if you can say much. Yeah, but that because I have been drawing straight line, right? If you do the second derivative, you know whether it's a curve or not. But I think that's a hard problem. I don't think. Yeah, I need to think more. We might be able to express that in terms of normally second derivatives in thermodynamics end up telling you about heat capacity and things like that. So it generally speaking, those are known as response functions. So it won't be just a state function, it will be a response function, which is a bit trickier. So that's what it is. But let me think about that. When I tell you all, remind me of something on Slack, please actually remind me, otherwise I will definitely forget. So yeah, you should remind me about this, okay? So yeah, so that's the solid liquid. Now let's go to liquid vapor. Liquid vapor is known as boiling, right? Same deal, dP by dt is equal to delta S by delta V. Now the enthalpy will be the enthalpy change in vaporization, right? Or in boiling, divided by the temperature at which boiling is happening, divided by the volume change during boiling. Heat, so when, for something to go from liquid to vapor, do you have to cool it or heat it? Generally speaking, you have to heat it, right? It'll be very strange if you cool something and then it became vapor. And for this one, even I don't know exceptions. I think this is true for everything. The delta vape H, which is defined as H of vapor minus H of liquid, this thing is positive, okay? You have to heat. How about volume change during boiling? Which is V gas minus V liquid. How positive? Generally very positive, right? This thing is going to be significantly positive, not just a small change, but a significant change, right? For most vapors. V gas minus V solid will be even more positive, right? Because solid generally tends to be less volume than liquid, except water. So this thing is very positive. So what does this tell us about dP by dt? That is going to be something which is positive divided by temperature, which is in Kelvin, therefore positive, divided by something else, which is positive, but a very large number. So this thing, first of all, is going to be positive, but furthermore, it will be a small positive number. It won't be too large because the volume change over here is such a big number, right? So let's go back to the phase diagram we had drawn, and we will keep adding things to it. So we had a pressure temperature phase diagram. In this pressure temperature phase diagram, we drew water, which was negative, and everything else was slightly positive, right? So this was water, and this was not equal to water, right? And we were talking about solid versus liquid. And now we are talking about liquid versus vapor. And we just said that dP by dt is a small positive number. So relative to the blue line or the red line, it will be relatively a flat line, right? It will have a positive slope, but it will be kind of flat. Okay, so that one is going to look like this. It will be positive, but not too positive, right? And you can see that's what happens in water phase diagram also. It's almost flat actually. So this thing is over vapor.
Solid for like on the left of the right side.
Yeah, sure. This is because I'm trying to talk about water and non-water also, right? For water, it is to the left. We can just remove this to be clear and just talk about non-water, okay? This is solid, okay? Now the final one is solid versus vapor. And we'll just do it on this page. Solid, vapor, same idea. This is known as sublimation, right? So dP by dt will now be delta sublimation H divided by T divided by delta sublimation volume. Again, delta sublimation H is positive. Volume change during sublimation is also positive. Most things, when they go from solid to gas, they really change volume a lot. And this is also going to be a very large number, bigger than 0, right? It will be almost comparable to what you had in the V gas minus V liquid, because for most things, solid and liquid kind of have the similar volume. It's gas which has much higher volume, especially as you go to lower pressure, the volume becomes more and more. So once again, this will be a curve that, let me use a different color, that looks almost flat. I don't know how to compare it really to the liquid vapor curve, but kind of the same. Okay, it will be positive, but very small slope. Okay, and if you look up the water phase diagram, you will see it's almost basically very close to. Actually, let's go to water phase diagram. Okay, solid liquid is very vertical, right? And you have to go to around this point to start to see how the negative slope starts to appear, right? But this one is not as flat as I drew, but it is still flatter with respect to this one, right? And the solid vapor is not even shown here. It's somewhere below. Is it? No, solid vapor is this curve, right? So that has almost similar slope as this one. But this is the steepest. That's the point that remains. This is the steepest. These two have gentler slopes than this one. Okay. Any questions?
So basically, can you go back to the phase diagram? So for solid liquid, the line is almost vertical up till like some really high pressure, right?
Yeah.
So does that mean the delta fusion volume is only negative once you reach that high pressure?
No, it is negative, but it's a very, very small number. It's close to zero. It's a super small number. And then that pressure things start to complicate because you have more solid phase transformations happening over there. This is really messy. This part of the phase diagram, once you hit here, you also have to worry about this solid competing with this phase. It's a whole different triple point up there. This is not the only triple point. This is also a triple point. This is also a triple point. This is also a triple point. There are many. Next time someone asks a triple point of water, you have to be like, which triple point? And if they do, yeah.
And then solid liquid, like that line is pretty positive. So
Yeah.
at higher temperatures, it's like the volume change is positive. Then?
Yeah.
With that other ice.
Yeah. Okay. So that gives you basic tool to think about boundaries in a phase diagram. That's the Clapeyron equation. Again, so let me recap. And we should be able to stop a bit early today. So Clapeyron equation said delta P by delta T is equal to delta S by delta V is equal to Q reversible by temperature divided by delta V. It's also equal to delta H by T delta V, right? And this is exact. And the proof just use dg is equal to VdP minus SdT, right? If you forget this equation, you just have to remember dg is equal to VdP minus SdT, right? That's where it comes from. You see the form, right? VdP minus SdT. So dP by dt has something to do with V and S, right? So it's easy to remember. Now we are going to talk about an approximation to Clapeyron equation, which is actually more widely used, especially by biochemists. They use it even without realizing that they have made a horrible error. They are basically assuming a protein to be an ideal gas when they do this. You see, you're all laughing. Let me see you in your scientific careers. When you get stuck, you'll be like, yeah, I'm just gonna go with ideal gas. So for this one, strictly speaking, it applies only to liquid vapor, but people use it for everything. You will see it. And if you go and look up Clapeyron equation on the internet, the first top 5 websites you will see, some of them, when I checked this morning, say Clapeyron equation, or also known as the Clausius-Clapeyron equation, and you scream. Like, it makes you so angry. So we are going to look at liquid vapor boundary. Okay. If I look at liquid vapor boundary, then dP by dt is equal to delta S by delta V is equal to the vaporization enthalpy divided by temperature divided by the change in volume during vaporization. Okay. So what I'm going to do here is to look at this thing, and this is V gas minus V liquid, right? That is exact. There is no approximation so far. Now comes the approximation. Approximation number 1. V liquid is much smaller than V gas. Okay, we just ignore V liquid. Approximation number 2, ideal gas. Gas is ideal, okay? Or V gas is equal to nRT by P. Okay, so if you do these things, and I again don't have equation numbers, so I'll just call it equation number 11. I don't think I went to 11, so it's safe. So put approx 1 and 2 in equation 11. What will you get? You will get dP by dt is equal to delta vaporization H divided by T multiplied by delta vaporization V. That is nRT by P, or dP by dt. Let me write down this equation on the next page. Okay, this one I'm going to write on the next page and just start from there. So what do we have? dP T by dt is equal to delta vaporization H by T delta vaporization V, and I have approximated it as delta vaporization H divided by T. The delta vaporization V, I'm ignoring the liquid altogether and I'm saying the volume is ideal gas, okay? So that is nRT by P. So this gives us dP by dt is equal to P by nRT square, P by nRT square delta vaporization H. Or if we rearrange terms, let's bring P to the left side. This gives us dP by P is equal to delta vaporization H by nR dt by T square, okay? Or d log P ln P by dt is equal to delta vaporization H by nRT square. And this is the Clausius-Clapeyron equation. This is approximate. This does not apply to everything, but it's used heavily, and people sometimes just call it Clausius-Clapeyron equation, which is simply not true. This is Clausius-Clapeyron equation. Approximation. It is an approximation to Clapeyron equation. So 3 years down, 3 years from today, I will see you in the lobby and you will be looking very happy, and I'll just ask you which one is more exact, Clapeyron or Clausius-Clapeyron. And if you don't tell me the right answer, I'll be so sad. So please remember this, okay? So any questions about this? Okay, so I want to tell you a little bit about the second midterm. I haven't graded your first midterm yet, but I still decided to be nice and give you a more enjoyable experience. So there will be around 7 or 8 papers. Okay, some paper will be related to biophysics or biochemistry, some paper will be related to some quantum materials, some paper will be related to water, so, and you have to present a report and a presentation on this, okay? And the way it's going to work is I will be splitting you into groups of 3. And
I know you said that you would do it rapidly.
Yeah.
But can I give back an argument?
Please.
So, I mean, here we all have like clear responsibilities and different schedules. So it's easier to coordinate when you're like in the same group, because at least you know like this once a week you're gonna be at the office at the same time.
Yeah, but then it does not allow mixing. It is an opportunity for you to know, like, oh yeah, that student who took the class with me, I know who they are.
I know them, I remember the names, but it's a matter of effectiveness, definitely. Especially now that it's reaching the end of the semester and we all need to doctor grader. Yeah.
I will think about it. So what do you propose?
I propose.
I like that proposal.
Then you're gonna pick Lydia, and she's going to pick Anjali.
Who knows who I'll pick?
I can tell already.
I could pick you.
No, I'm not going to do it. I'm done. I have tenure. I don't have to tell you. Sometimes I have nightmares like, oh my God, exam is about to finish and I haven't done everything. And then I wake up, oh, I'm done. No worries. I have no promotion left. Oh, good.
So, before you say what you say, it's just a matter of like, it's easier just to coordinate.
But you also miss out on something. So,
I mean, we can have like a social event and then we know each other, but for the exam, definitely we
no, I want to do it randomly. You have to know each other, sorry. It's going to be random. And you don't have to, she's looking very sad.
Yeah, I don't want to.
Fine. Maria Delia wins. Okay, so it won't be random. You can pick and we'll figure out how to do it. But I must say that if this leads to 1 or 2 students not getting a group, then I might change it, okay? So most likely it's going to be you can pick, but if it's leading to some sort of thing that I don't like, and then I'm going, okay, I reserve something, and in that case, don't get upset. Okay, I will try to make it normal, and one way to deal with that is, so even with this arrangement, I mean, this time it's actually possible because students are from chemistry, chemical physics, biophysics, and an undergrad. I mean, what we're gonna do about him? How can you match his schedule?
He's gonna go for the 10 people.
You think so? Okay, we'll see that.
He's like a major, right?
And do we have any other majors apart from chemistry, chemical physics, biophysics? Okay, that's better because last year I had mechanical engineering, I have had applied math, that makes it complicated. So now we can do it. Okay, fine. So you will be in groups of 3 decided by you. Good. Now I expect even better work. Okay, I'm gonna be harsher in grading. Keep that in mind. Huh? You have a problem with this? He wants it to be done. Okay, we are going to do a poll. Okay, how about this? We are going to do a poll and democracy shall prevail. Fair enough?
Yes.
And if you don't respond, then you don't have a vote. So please vote. The poll will be set up and you have to vote and it will be demo. And if there is a tie, then Pakora will cast the tiebreaker. No, I will offer him 2 treats and we'll see which treat he picks. Both groups can offer treats for Pakora. If someone's birthday is coming up, you can bribe him. It will be very fair. Okay, no, I see, right? I can see merits of both sides. Random is nice because you get different stewards' ideas. The other reason why random is nice is because, let me get to the next point. It also leads to discussion in picking the paper, right? If you have all biophysics students, you're definitely going to pick the biotype paper. When I have seen lots of fun interaction happening with this. So we will decide, it will be democracy and no one can complain. So then you will be in groups of 3, random or not random, we will see. And then you will have to meet together to decide which paper, okay, argue. And I can promise you there will be arguments in this and don't go for the shortest paper. The shortest paper will generally be the most complicated paper, okay? If you read a paper from Science or Nature, they are the worst papers to read because it's like a magazine, right? 1 page and then the 30-page supplement. So don't just fall for the shortest paper. Journal of Chemical Physics, Journal of Physical Chemistry papers are sometimes the best paper. This is also good advice for all the chemistry students when you do a literature seminar. Don't pick Science or Nature papers, okay? Pick like trade journal papers. The Science or Nature papers, generally they also use so many techniques in order to get into Science or Nature, right? It's never just one technique. It's like we do NMR, we do molecular dynamics, we do density functional theory, we do everything. And some committee member will ping you. It will happen. So pick traditional papers, okay? So you will pick a paper, you will prepare a 1-page report on it, and I will specify the details on what 1 page means and everything. And I'm actually going to be strict on the 1 page because that's what applies to your future proposals and things like that. When you submit a proposal to NSF or NIH, if it's 1 line longer than the 1 page, they will decline it. And guess when they will decline it? 5 months after you submitting the proposal. It has happened to so many people. Your font size was not 10, it was 11, declined. Normally it goes the other way, right? People use tighter font size to squeeze it in. So I will tell you precise rules and you will have to follow them. The presentation will be a group presentation, and this is where not doing it randomly might help. You have to prepare slides and you have to prepare a video, a 5-minute long video. It could be a Zoom video. I want all people to speak in this video, and it will be posted online, not like on Twitter or anything, but in Google Drive, so you can all see it. And that's how you will be graded. I intend to be very lenient in this, so please don't screw up. It's easy to get marks in this. Okay, just go through the paper, do what I'm asking you to do. And normally people enjoy. I do this in StatMech and in Chem 481. Also, people enjoy this experience because you see like why all these complicated equations actually have huge impact in science, right? You can do a variety of things with this, right? So that's how the midterm will be. I will be giving you 1 class off for sure to do this. So if you have an enormous scheduling problem, you at least know there is 1 class where you can meet and discuss it, right? Now, whether that class will be the Tuesday before Thanksgiving or the Thursday before Thanksgiving, I don't know. That depends on my seminar schedule, unfortunately. I have to give a talk on Thursday and a talk on Tuesday. And one of them will clash with this class. So, and that's what I will let you know soon. And
All the classes are gonna be in person. I saw you post that.
oh yeah. No, Chicago. Chicago is on Friday. So no. I will teach and then go to Chicago. Then I come back, then I have to go to Caltech, and that clashes with this. That's the problem. So I might teach from Caltech on Zoom till 8 a.m. in California. So yeah, I will figure it out. We will be missing at best only one class. We are doing okay on pace. There will be one more homework after the fourth one. Please try to do it. You know, as I said, your worst homework won't matter at all. And I'm going to give you bonus points on both of these. If you get bonus points, it can make up for your poor performance in the midterm. I'm not saying that you have done poorly in the midterm, but you might. And the final will be in class. And yeah, anything else? Okay, so see you. You have a question? 5 minutes total. Who's going to watch 15 minutes per student, per group? I go crazy. Okay, see you next week.